Our next guest who is getting his presentation ready there is Karl Hedrick from UC Berkeley, and he's going to give us a good presentation here. I'm looking forward to it as soon as we get this rolling here.
Yeah, how I get it on the screen? I've got to
Hold on just a second. Let's see if we can just do that by pulling it. Can you use your mouse to advance?
Yeah.
There you go.
Okay.
Okay, well, do you want to see if your mouse is going to work right there?
I doubt if it does work up there.
Well, I can advance for you. You just tell me.
There's a couple we got to click on the videos and we'll
I'll see if
deal with that. Thank you. I'm Karl Hedrick from UC Berkeley, and I wanted to talk about some work that we've done over the past decade. It's primarily with military application. Most of the research that I've done has been sponsored by the Office of Naval Research. I do this in conjunction with a professor there in Raja Gupta, and we've been working quite a few years. I want to talk, and I think there's some significant crossover applications to civilian applications. The three words that were on the last slide were autonomy. So I'm talking about autonomous behavior, not remotely piloted vehicle. The motivation of the Navy at that point was that they had a lot of applications where the soldiers were too busy to be able to be in a trailer somewhere flying UAVs. So they wanted to move it up to a higher level where the human just says he wants information. He wants a picture of that area. He wants a given area searched. He doesn't care who does it. He just wants to ask for information, have the information come back. And so that was the autonomy area. The cooperation word there meant that we have a team of UAVs, multiple UAVs, that had a communication capability and they could talk to each other. So they are cooperating. Collaboration is a more serious form of cooperation. Collaboration where you have a team of UAVs that are sharing a task. So in a search and rescue task, you might have where they are searching the field, they divvy up the field, they let each other know what they're seeing, and so the collaboration is the final area that we've done quite a bit of work on. Some of the benefits of UAV collaborations were to try to go to a lot smaller UAVs, not to have the $1 million, $6 million Predator type drones, but to have not really disposable as it says here, but to be able to have UAVs that if you lost one or two, it didn't really matter, that they can continue to do their tasks. You could have multiple tasks, multiple targets. You could have new tasks come in, new targets come in. And then what we were doing at Berkeley was trying to set up an architecture that could handle this kind of a network of UAVs. Next. When we first got into this about 9 years ago, we had a UAV, just a Sig Rascal, I'm sure you've all seen. We bought an autopilot from CloudCat, a Piccolo system that I know all of you know about. And when we first got it, it was a ground station control. So the control of the UAVs were actually done on the ground station on the ground. And some of the applications that we looked at there was convoy protection. We actually flew a convoy protective mission in Fort Huachuca in Arizona. We were told they tried this out in Iraq. I don't know if that's true or not. But the idea was we would have a ground station in one of the convoy vehicles that would be sending up GPS signals and actually setting up trajectories so that all the trajectories were computed on the ground station, and then they were radioed up to the UAVs. And that one we actually flew. I'll show you just a pretty bad movie of what we did there. We also worked on a search and rescue mission for the Coast Guard that was never flown. But the idea here was to say we're going to have UAVs essentially like wingmen that the ground station is in the helicopter. There's a person in the helicopter who's got, let's say, an infrared camera looking out to see if he can find a downed pilot or a capsized boat. And you would essentially have increased sensor coverage by having UAVs flying alongside in a pattern and providing information to the human inside of the helicopter. What we do at Berkeley is develop algorithms. We don't build UAVs. But we like to flight test our algorithms. And so we have a number, we have two major types of UAVs, the sUAS and the MLB BAT-4, which has now been moved into more fancier bats. But I'll show you some of the covers that we did with that. And certainly perimeter surveillance, border control. I think these sort of algorithms are fine for the master-slave, what I call master-slave mode, which means that we have a ground station on the ground, which is the master setting up commands for the UAVs that are the slaves. From the get-go, we wanted to have more intelligence on the UAVs. So we moved, at that point, PC-104s, we put them into the SIG-RASCL. We had path computation, we did task allocation and path planning on board the UAV with the PC-104s. We were trying to get away from total reliance on GPS, so we had a lot of computer vision where we would say try to track a river. I'll show you a video of that when we get into it. So let's move on. This was the algorithm computed on the ground station. You can have the convoy here moving along. So you'd like to have, and the assumption here, of course, is that the UAV can move faster than the convoy. So we have a trajectory here. The important part is to match the longitudinal velocity while giving the UAV chances to fly around. The nice thing about the UAV for us was we could fly them at different altitudes, so we didn't have to worry about air collision. Next. This is, again, some rough footage. There will be two types of cameras here. We had two UAVs. One had an infrared camera, and one had just a regular, ordinary video camera. You'll see shortly that UAVs come in. We have to have better resolution if we were looking for incendiary devices and things. But we were able to show that we could pretty simply, and again, this is a master-slave where all the computation is done on the ground station in the convoy. And we switched back and forth between the regular video camera, color camera, and the infrared. This was the experiment that was done in Fort Huachuca. Okay, next. So the concept here was that we would have somebody, a warfighter, a human being that wanted information. He wanted to create tasks. This could be search an area. I want to move my troops over the hill, go look over the hill and see if there are any bad guys there. So we had to develop a capability for the user to be able to communicate to a laptop what he wanted to have done. We developed a computer language to do that, which I don't want to go into here, a graphical language that can be computed to XML rather automatically. So we were able to say, take rather complex tasks. They could be conditional tasks that said, go to spot A, take a look. If you see a tank, then do this and then do that, if not. So you can make it a rather complex mission. But then this mission would be communicated to the agents. Some were within range, some without range. The agents then would decide among themselves who would do what task. The human says he wants a picture of that area, and then the agents themselves will figure out which is the closest one, which one has the right camera, whether you need an infrared, whether you need a normal camera, whether it has enough fuel, enough sources. But we're constantly designing so you can be an agent out of range. This UAV over here may be out of range with the ground station. So we were trying to shift. The ground station now only function was to communicate the human's mission to the UAVs and then wait for the information to come back. Next. This is, again, close to 7-8 years ago. We had a Piccolo ground station operating on a 900 megahertz radio. We added PC-104s to do vision processing, path planning, task allocation. All the heavy-duty computing was done on board PC-104. All the UAVs were communicating with each other via just at 802.11. And this was nice. The 900 megahertz had a very low bandwidth, but it had about a 25-mile range. So we could send up these mission statements to the UAVs. The 2.4 gigahertz allowed more complex. We were doing probabilistic searches where we had to send the probability map and share that between the UAVs, which required a lot more bandwidth than was available on the 900 megahertz. Next. Don't click it yet, but you're going to have to click on this, but let me explain it first. This is an actual mission that we flew at Camp Roberts down in Southern California. And we were trying to make it, we're not graphical user interface people. That's not what we do, but we had to do it because you had to fly the UAVs. So the idea, we had 3 UAVs that were in the air at the same time, Big Blue, Polar, and Kodak. And we had a ground station down below communicating with them. So you can see Kodak, Big Blue, and Polar. They were up there just waiting to be told to do something. A human's going to come in, and there's a mission task where he can look on that, and there's a table of missions that you can do. You can search an area, go to a point. You see some of them here. So what the human's going to come to do is come in and pick a mission. All 3 of them are going to do it. Then he's going to say, well, I'd really rather have another mission done at the same time. And so one of them is going to go out and do that. And then he's going to make a third. So at the end of this, there'll be 3 missions going on, 3 tasks going on at the same time, with the UAVs deciding. And really, we were making pretty simple decisions. Who's the closest? We were not doing who has the right camera and who has enough fuel and that sort of thing, which you have to do in a real situation. If you can click on the in the middle there. Oh no, you got to click in the middle. Go back. Can you move the little arrow around? There it is. Click on that. All right, here they go. These guys are just going around trying to stay out of trouble. Here are the border patrol is what the human asked for. He then goes over and sets this up. That's what he wants to have searched and just fly over and see if there's anything there in a continuous fashion. So these 3 guys very simply say, okay, we'll split it up into thirds. You can see they pick the third points, and they're just going to fly around and stay there looking for something until the human tells them to do something else. Now, pretty soon the human's going to come in, and I hope sooner than later. Here he comes. So he's going to say, visit a location. He's going to go over here and put the location that he wants visited. And so they talk among themselves now, and basically, he tells you that you're using resources, and he says, okay. And so the closest one to that task at that particular moment is now going to go over and take a picture. And this is task 101. That was task 100, which was border patrol. This is task 101, which is visit a location. And so these 2 guys have figured out that they can split it up into halves. So they've split the border up into 2 halves, not being told by the human to do this, but just because that's the right thing to do. And now we're going to get the third task going to come in, and he's going to ask to do another border patrol. And I think he's going to look at the river down here. And later on, I'll show you how we found the river using vision and not GPS. And then he says, go execute that patrol. It's telling you you're going to take away assets. You say, okay. And so someone's going to come over and do this. I think it's Polar here is the closest guy. I'm actually not sure if he's going to take it. Looks like he is. So I think you get it. If you can click off of the thing now. Okay. Now this language, again, I'm not going to go into. We developed this language. Raja Gupta was the primary person who developed this language. We did some applications that was very simple. You could do it with a pull-down menu. We did some demos that were big on YouTube 6 or 7 years ago. Now there are a lot more complicated YouTube things you can see. But basically commanding a mission with your cell phone. So you could say, if we had these flying around, you could put a mission in here. You could do it in Washington, D.C. and control something happening in California. Next. Again, this is a little more maybe than you're ready for, but basically this is the way we vision a UAV. There's a low-level controller which follows GPS points, waypoints. And so this is the autopilot for us. We have an autopilot that we didn't develop, we bought. You have a path planner. We do a lot of the algorithms for our path planner. It's a task allocation and path planner combined. And then you have to have a communication that sends out and communicates with the human as well as communicates with the other UAVs. And then you have to have a transition condition logic which says I've done this, I've finished this task, now I gotta go to the other task. And I think that's all I need to say on that. This is a wonderful chart, I'm sure you find this intriguing. The point of this is each UAV has this matrix in its memory, and there's 4 quadrants. This quadrant is what if I'm the UAV, this is what I'm doing. This is a particular task I've got, this is where I am right now. This is when I started the task with a timestamp, but essentially this keeps track of one UAV that it's on. This is what all the other UAVs are doing, so I know that what they're doing. So they're taking on tasks, I'm taking on tasks. These are the tasks that are left. So when I finish my task over here, I go over here and pick some of these out. And these are the tasks that are done. So when everything's done, there will be nothing here, everything will be here. Pretty simple logic or an architecture, but it's one that seemed to work pretty well. Next, this is something that the mathematicians at every university love. It's they're trying to say, I've got so many agents or UAVs, I've got so many tasks. What's the optimal way to assign agents to tasks? They give this the name the multiple traveling salesman problem. And to do it, the traveling salesman problem is saying, I've got all these cities, I've got all these cars, I want to finish going to each city in minimum time. How do I do it? That's a really tough problem. And you can't do it in real time being a second or a minute. You could do it if you had several weeks or something. So we've done a lot of work on approximate allocation algorithms. The Navy was not so much interested in optimal algorithms, they just wanted a task allocation procedure that worked and got the mission done. And we had that, and everybody has been trying to improve and make slightly better algorithms. But this is a fun area, particularly for universities. Next. Now this is the idea of cooperation. I know this is a wonderful thing here. The idea here is you've got 2 airplanes looking for this cactus. Now if you really wanted to figure out what's the trajectories these 2 guys should take to minimize it. I don't know that the cactus is there. I have a probability map that says what the probability that it'll be there. This is another tough problem that I couldn't do in real time. So we did it in what's called a greedy way. So click this. Click it once again. Can you click? Yeah, anywhere. That's fine. So this guy says, I don't care if there are other UAVs. I'm going to plan my path. I'll take the most probabilistic path. I'll go to the areas where the probability is the largest that I'm going to find the cactus. But then he click it again. He then communicates his path to his colleague over here. His colleague now doesn't want to just repeat what this guy's done. So click it once again. So he then chooses a path conditioned with what the first guy has done. So he says, okay, I know this guy's doing that. I'm going to presume he's not going to find it because he hasn't told me he has. I'm going to take another path to get there. This is not the optimal way to do it, but it's a way that you can do it and do it in a computational framework that works. Next. Now before you click on here, I'm going to ask you to click on here in a moment. This was down at Camp Roberts. This is the probability map. It looks a little jagged, but this is a uniform probability. We told 2 UAVs that there was a truck on the runway, and this is the main runway, and these are 2 side roads, and it's equally probable that it's there. And you'll see there's going to be entering. This is a real flight test, not just a computer graphics going on. They're trying to calculate trajectories that will take up the most area. So this is the probability, it's called the probability area. So what you clearly want to do is take this path, but then if you're his colleague, he's got that path, you have to take something else. So you can click on it. Nope, go back. And click on it. Yep. So here they go. I can tell you what these little dots are, but that doesn't matter for right now. They are flying at different altitudes. These are real UAVs. The interesting thing, this guy seems to be hogging all the action. He'd like to get over here, but he's got a finite turning radius. He's got a big wind acting on him. So he can't. So this guy comes over, and this is where I have to tell people they're different altitudes. Or too good. Okay, next. This is the Sid Rascal. This was our first guy that we bought. We bought about 5 of them. This is the guy we had to put a payload tray in, PC-104 payload. We could carry maybe 10 pounds of payload, maybe not. But we've done an awful lot of tests for that guy. And then next, this is what I used to have a slide that said the Berkeley Air Force up there. We bought these from MLB. It was their I think it was their first bat that they had, or one of their first bats. We had these designed. We worked with Steve Morris on the design of this. Most of them had gimbals. It was a pusher aircraft. It could carry up to 25 pounds of payload. It weighed about 100 pounds. It could stay up for many hours. So we use this quite a bit. Its stability, its flying characteristics were not so good. It's a very hard plane. It was sort of rudder controlled, and the ailerons really didn't work very well. But I think they've improved it a great deal since this guy. Next, this is, I'm sure this is ancient now, but this is our PC-104 boards. We were terribly proud of this with the 802.11 card in there, and we had these cards representing different functions, vision, path planning, and so forth. So this again has been replaced, probably something now about that. Next. This is Camp Roberts, which we haven't used in 2 or 3 years. We've moved into more of a theoretical area, and we can do a lot of our experimental work using quad rotors and things other than real UAVs. We still have some of our fleet of UAVs, so we haven't flown it. The Camp Roberts facility was an excellent thing for us. It's the Army National Guard, California Army National Guard. The Naval Postgraduate School has a UAV runway on it. It's got great facilities. They charge a little bit of money, but not much. But this was a great place to fly. We did this for about 5 years in a row. Next. Okay, this is my final movie here, and I won't show the whole thing, but this was our first demonstration of being able to have one human, our program manager, named Mark Steinberg in Washington, just tell him that he could control 4 UAVs in the air at the same time. So we had these 4 guys up in the air. The first thing I think you're going to see is our water. This is primarily trying to say that we wanted to get away from GPS. We wanted to be able to find the river. So let's click on it, and then we will not watch everything. So this is our little fleet. We're going to start off not on the Camp Roberts field, but nearby because we wanted to be close to water. And here he is. This is a near-infrared camera that you'll see some data from. This is kind of an exciting project. This was human flight here, or controlling it. He was a real good pilot. We almost lost everything there, including our own program. But he's now not using any GPS. We put him on a circular route, and he had done the visual segmentation to be able to tell the difference between water. You can see it here. The yellow is the water. Instead of flying to the center of the water and then planned a path. So it wasn't just detecting water, it was following water. And this worked extremely well. It was pretty simple. The differences were pretty simple between water. This is on the CloudCap software. You can see we're doing pretty well. There are some issues when you come up to forks and so forth of what happens. But that's about it. I think that's actually good. I can show you some of the other 4, but it's not that exciting. So I think I'm going to end it right here. Thank you very much. Any questions? Yes?
Do you see, sort of looking off into the future in terms of the general technology of this field, do you see things bifurcating in terms of human control versus autonomy, or do you see things definitely going more one way or the other? Just talk about kind of your vision.
Yeah, that's a hard thing for me because I love autonomy. That's what universities do and so forth. We got a little dose of reality. We worked with the Naval Special Warfare down in San Diego. They had all these Scan Eagles, and they told us that their people didn't have time to put down their gun. They really wanted to have some autonomy going on. And so we developed a whole thing for them that we thought they were going to put on Scan Eagles. They finally decided, I think, that it just wasn't reliable enough, and that you just got to keep the human there, and they sort of lost interest in autonomy. So I think autonomy is still a vision that they have, and I think even the military thinks that someday we're going to have autonomy. But a lot of the people that are doing the remotely controlled work are former pilots, and so. But I think personally think that it has a great future, particularly in civilian applications, where you're doing really boring things. You're watching a bridge, the Golden Gate Bridge, 24/7. And you don't want to have some guy up there doing it. So just having a very simple autonomy. I mean, you can get pretty fancy with autonomy, but a simple autonomy just says, here's a repetitive path, just fly that path, and tell me if something interesting happens. Being able to have automatic crop dusting. There's a lot of applications like fire, being able to fly your UAVs in the center of a forest fire. You'd like to be able to have some autonomy there. So I think there's a future for it. Probably, I think you'll see it soon if the civilian sector and the FAA gets things settled. I think you'll see it sooner in the civilian sector than you'll see in the military. Yes?
If I could comment on that, in the international community, in the ICAO division, there's no such thing. They are not going to accept fully autonomous UAS, period. And you always have to, and even here, when you design your systems, you need to make sure, even though you have an automatic system where you let the airplane fly GPS waypoints and stuff, without flying, you always have to be able to take control of your, because of a lot of the, being able to clear for intruding aircraft and taking the base of the new derivatives aircraft. Except in the lost flight scenario, the FAA is actually accepting, I think it's in current language, that that's not a normal situation. So the way they word this is, in normal operations, you have to be able to take control of it. Doesn't include automatic flight, which most of these systems are, but it does preclude truly autonomous flight, where the aircraft is making its own decisions as you as a pilot and have no way to take control of that aircraft. That's just a point of design system. Because I was at a meeting in Atlanta, and some fellow was, academic guy, was talking about how he lets his airplane just go fly, and he had no way to do anything about it. And he was going, oh my God, what a, GA aircraft thing, he couldn't make it fly like a bird and get out of the way. So that's the point.
Am I correct? I heard that the ICAO nomenclature was going to be pre-programmed aircraft. Did you hear that?
No, the way I understand it is, that's why they went to the term remotely piloted aircraft, because everything we're talking about here is pretty remotely piloted, right? You can take control of your aircraft. It's this other branch of UAS. UAS is the top level. Remotely piloted aircraft is down one stream, and truly autonomous aircraft are down the other. Well, ICAO is saying no truly autonomous, where it's making its own decisions, artificial intelligence, all that stuff. This is not a player, at least for a while. And for a while, I look at it, it's not in my lifetime. Okay, that's going to happen. But and that's why we in the industry, at least in I think, we started to use the term on that, because this term autonomous has generated probably thousands of hours of discussion with Alpha, helicopter guys, and whatever. So I'm on a campaign to change the term to automatic versus autonomous.
I just make a comment here that there's a parallel effort going on with automobiles, as you probably know, the Google car and so forth. Legislation in California that says it's all right to have I don't know the term automated or autonomous is used. All of the automotive companies, it's really surprising. I work with several automotive companies, and they have autonomous testing. They're doing research, and they think that within 50 years, all of the automobiles are going to be autonomous. The real question is whether does it have to be a human in the Google car now? It has to be a human sitting in the driver's seat. But the question is, I think the human can get out of there and go to sleep at some point. We'll see. Okay.
All right.
Thank you.